Behind every great result, there is a hidden process most people never notice. Welcome to the channel. Today, we are diving deep into this fascinating world to see how it actually works.
Imagine pulling a standard coin out of your pocket, dropping it, and watching it suddenly turn into a black hole right here on Earth. But before we let it hit the ground, we have to pause. In astrophysics, the word size introduces an immediate problem. A black hole's size refers to the diameter of its event horizon, the absolute point of no return. Because these objects are incredibly dense, defining one by the dimensions of a coin can mean two completely different things. The way the world ends today depends entirely on whether this hypothetical black hole has the mass of a coin or the diameter of a coin. Black holes pack matter so tightly that physical dimensions are decoupled from weight. That single distinction creates two completely distinct timelines for the destruction of Earth. Let's start the clock on scenario A, a black hole that weighs exactly as much as a 5-gram pocket coin. This scale comparison shows just how small that object would be. A 5-gram black hole has an event horizon of 10 to the negative 30th meters, a fraction of the width of a single atom. At this microscopic scale, a quantum process called Hawking radiation takes over. Smaller black holes constantly lose mass, which means our object instantly begins leaking energy. Because its gravitational reach is far too small to pull in the matter around it, it cannot sustain its mass. It evaporates almost instantly, vanishing in roughly 10 to the negative 23rd seconds. This photograph of Albert Einstein reminds us of exactly what happens when that mass disappears. Under Einstein's famous equation, E equals mc squared, all 5 grams of the black hole's mass are converted directly into pure energy. A 5-gram mass conversion yields roughly 4.5 times 10 to the 14th joules. In explosive terms, that is roughly equal to 100 kilotons of TNT. Looking at this photograph of the flattened rubble of Nagasaki puts that yield into historical perspective. 100 kilotons is roughly 3 times more powerful than the atomic bomb dropped on this city. In scenario A, the black hole detonates in a blinding flash. It wipes out the host city and leaves a massive crater, but the rest of planet Earth survives perfectly intact. Now let's reset the clock for scenario B, a black hole where the event horizon itself is 20 times across, the physical diameter of a US quarter. To reach that diameter, the object requires a specific extreme density. This visual equation shows the reality. That tiny coin-white sphere contains slightly more mass than the entire planet Earth. The moment it appears, Earth suddenly has two competing centers of gravity pulling against each other. Because this black hole is a billion times denser than our planet, it instantly plunges straight through the crust and toward the core, oscillating back and forth like a pendulum. As it swings, it creates an accretion disk. The black hole pulls rock, magma, and the atmosphere into a superheated, swirling ring of material that orbits its center, consuming everything in its path as it carves through the planet. The sheer friction and intense gravitational compression of all that material release blinding, highly lethal X-rays and gamma-ray radiation directly into the surrounding mantle. The Earth would literally cook from the inside out. Within hours, its orbit around the sun would destabilize, leaving nothing but a fractured, radioactive debris field orbiting a tiny, invisible point of consumption. We are left with two completely different ends to the same thought experiment: a localized blast crater versus a shredded, molten planetary graveyard. These outcomes reveal the true nature of black holes, dynamic objects whose behavior is dictated by specific physical thresholds, rather than a universal vacuum-like appetite. The rules governing these objects change wildly based on their scale. At the microscopic end, they are governed by quantum mechanics and leak away as Hawking radiation. At the massive end, they exert absolute gravitational dominance. The scale of the universe is deceptive. A hypothetical scenario involving a pocket coin contains enough physics to vaporize a neighborhood or devour a world. It all depends on how you define its size.